Hi, it's me, Wei Dang, and today actually I wanted to give a presentations of making a predictive model to predict the Walmart sales based on the previous sales information that we have. And I wanted to build a model based on the optimization procedures that we learned from our optimization class. So in order to let you guys have a better understandings of the optimization procedures and the modeling construct methods that I'm going to use in my presentations, I wanted to give you guys some background information of those theory that I might be used into my optimization presentations. So the first theory is regressions. So for regressions in statistical modeling, regression analysis is actually a statistical procedures for estimating the relationships among variables. It includes like many techniques for modeling and analyzing several variables when the focus is on the relationship between a dependent variable. Sometimes we will call that a predictive variable, and for one or more independent variable, which sometimes we could call that's the predictors or the explanatory variable. So a really easy examples of the regression would be you wanted to understand whether height it's positive correlated with your age. So so you set your height as a dependent variable and you set your age as an independent variable, and you're trying to get a lots of data from different places, and then you're trying to analyze your results and see whether they have correlations between the two variables, and that is basically what the regression is for. It is for simple applications based on my example. So the next background information I wanted to provide is Newton's method. So actually what it says is one starts with an initial guess which is reasonably close to the true root, and then the function is approximated by its tangent line. And one computes the x-intercepts of these tangent lines. The tangent line would typically be a better approximation to the function's root than the original guess, and then the method can be iterated until we think we can't iterate anymore. I mean, until we find the optimal value. And whether or not we can find the optimal value, it depends whether the functions that we're trying to iterate is convex or not. And the third theory I wanted to introduce would be backtracking. Backtracking is actually it's a general algorithm for finding or some solutions to some computational problem, notably constraint satisfaction problems that incrementally builds candidates to the solutions and abandons each partial candidate C as soon as it determines that C cannot possibly be completed to a validation solutions. So that is something about backtracking. It just like keep finding the solution until it satisfies some types of constraint and things like that. So yeah, and I hope this could help when I'm making my optimization presentations, because I'll use a lot of these theories. Good morning, everybody. My name is Wei Dang, and today I'm trying to make a sales prediction with the optimization procedures. So now let's move on to our agenda. So I'll briefly talk about what I'm going to do within the following slides, and also we'll discuss what types of data we're going to use and how I'm going to organize the data, and then I'll move on to the model I'm trying to use for prediction purposes. And after we decide what types of model we're trying to use, and then we will move on to the optimization procedures that we are going to perform. And after we have the optimization procedures, we'll test and compare the performance of the two different optimization procedures, and we'll make our conclusions in the end. So here is our introductions. The purpose of our study is actually to use optimization procedures to predict the 52nd week Walmart sales or Walmart store sales. And the model we are trying to use is linear regressions with multi-variables. And the optimization procedure is minimize some square error and minimize some absolute deviations. And we will talk more about this in the following slides in more details. And let's discuss about our data first. The data is actually come from Kaggle.com. It's a Walmart sales prediction project, and the structures of data, it's really simple. It just contains a few columns, and here is the sample data structure I attach on the right table, which contain the first column is the weekly sales, and the second column is actually the days of the week that the sales occur, and then the third column is actually the size of the store, is the store volume, and the last column is actually the types of the store. It's actually provided by Walmart.com. And then in order to actually make a multivariable regressions, what I'm trying to do is actually to use the previous store sales to predict the future store sales. So I have to converge the data into different weeks in order to make my autoregressive linear model. So after the transformations, the new structures of data is attached on the right side, which contained the week sales from week 1 to week 52, and also with the combinations of the store size and store type, and also I added an year variable in the end so that I could specify which year of that week is it, which year is that week, so that I could make my regression analysis more convenient. So after finished talking about my data, and I'll move on to the model construction procedures. So I'm trying to use the lag of 4 to predict the 52-week store sales. So I'm trying to use the week 48 to week 51 as my lag, and also with the combinations of the factor variable, store type, and store size for my linear regression model. And after we have our linear regression model, we could start to talk about the optimization procedure we're trying to use to find the optimal value of our multivariable linear model. So the optimization procedure would be to minimize some square errors and minimize some absolute deviation, as I mentioned above. And the way I find the optimal solution is trying to use iteration methods through backtracking with the implementations of the Newton steps. So let's talk about the minimize some square error optimization procedure first. So first we have our objective functions, and since the objective function is a quadratic function, so I believe it is a convex optimization problem, so that we'll be able to find the unique solutions for our data. And after we know our objective functions, we also need to know the gradient and the Hessians of our objective function in order to find the optimal solutions. So here is the so we have to write the closure functions for our sum square error functions. And here on the left side is actually the matrix form of the sum square error functions, and on the right side is actually the sum square error closure function in our code. And after we have our closure, have our sum square error closure, and we need to calculate the gradient closure in order to move on to Newton steps. So on the left side is the matrix formats of the theory gradient closure functions of the of the least square linear functions, and on the right side it actually shows the R codes of the gradient closure. And after we calculate our gradient closure, finally, we need our Hessian closure, and which is, in theory, which is the 2 times x the transpose times x. And on the right side, also, the R code is provided. And after we know these three different types of closure functions, we can start to implement that into our backtracking algorithms. So for the Newton steps, the iteration conditions would be provided on this slide, and also I coded into R, which is provided on the right side. And after we have our backtracking algorithm, now we need to initialize our input matrices. And for the X matrices, we'll have the intercept and also all those multivariables that I mentioned above for our model to construct our X matrix. And also for our Y matrix, which is our predictive value, would be the week 52 store sales amount. And also initialize our beta to 0 first. And we have to call our functions f, df, and d2f for the linear closure, gradient closure, and Hessian closure. And for the backtracking algorithm, I'll set the alpha to 0.3 and the beta to 0.7. And now we can start to run our 1000 Newton steps and see whether the sum square error would minimize and converge in the end. So on the right side graph, we can basically see the sum square error decreases rapidly after the first steps after the first Newton steps, and it starts to converge probably in 250 steps. So which based on this graph, which I think our algorithm works pretty well, and we finally find our unique solutions. And here is the table of the least square regression result. And based on this table, I think the linear model is a plot place because all the variables are significant based on the table, because the p-value are all less than 5%. And also the R square is about 90%. So which means the R square tells us actually the model fits the data pretty well, because it explains about 90% of the variance from this model. So I think this is a great approach. And also we're taught about the second optimization procedure for our linear model, which would be the least absolute deviations. So the objective functions of the least absolute deviation would be to minimize the absolute values of the x beta minus y. And we sum them all. And for this problem, I used the R package, which is called mass, to calculate, to do the iteration step for us. And on the right side, actually, it tells us the beta, the variables that all the variables that from the least absolute deviations are all statistical significance. So which means for this optimization, it's also a great approach for our model. And in order to know whether which optimization procedure would be a better suit for our case, and now we have to visualize the results of the two optimization procedures. So here is the performance summaries of the two optimization procedure. On the left-hand side, it shows the performance summary of the minimized sum's absolute deviation, and on the right-hand side, it shows the minimized sum square error performance, visualization performance. So based on the graph, it could really easily tell us both models have a really great results, because their 95% interval actually cover most of the actual data points. And for my preferences, because the range of the minimized sum absolute deviation optimization procedure is a lot. It's the range, the confidence interval range for the left-hand side, it's much smaller than the right-hand side. So which means I would say I would prefer to use the left-hand side one based on the range of the confidence interval. But both model actually works pretty great. So this is the basic summaries of the two optimization procedure I perform in this case. So here is my conclusions. The Newton step with the backtracking algorithm works in this case. And both optimization methods, which is the minimize sum square errors and minimize absolute deviation, can actually yield a really great result for the Walmart store sales predictions. But for our case specifically, I would believe the minimize absolute deviation seems to be a better approach for this problem. And thank you for listening. That's all. Hi, everybody. Thank you for your time reading my optimization presentation. So based on my presentation, it already shows the optimization procedure I choose to use are actually really efficient. So what we are trying to do right now is actually to talk a little bit about the model's improvements. So first, in order to know how we improve our model, we'll start to plot the diagnosis plots of those linear regressions we made. So first, this is the sum square error residuals plot, the diagnosis, the sum square error least regression residual plots. So based on these plots, we could see the residual versus fitted value plots does not seem to be that good because it does not seem random at all. And also we could see there is some obvious trend on those plots. So we might probably thinking about like how we might probably have to find a way to actually to clear or trying to minimize these kind of problems. And also the normal QQ plot does not seem the residual is normally distributed. So what we could do is actually to trying to find a way to find a way to make the plots get it back to normal. So we'll talk about the improvement procedure in the following slides. And secondly, let's take a look at the sum absolute deviation, which is the robust regressions diagnosis plot. For this plot, for this diagnosis plot, it seems to be better than the least square diagnosis plot because the red lines of the residual versus fitted value is really close to zero, which means that the expectations of the epsilons is quite close to zeros, which is one of the theories of a regression model. And for the normal QQ plot, it seems normal. It seems better than the least square line. So for me, based on my opinion, I would still stick with the robust regression model based for our case. So let's talk about some of the improvement procedures for the modeling constructions. So for normality problem, we could probably use a bootstrapping procedures to trying to bootstrap resampling procedure and trying to see if the residual could get back to normal after this procedure in order to so that we could see whether the results could, the prediction accuracy could be improved. And for the randomly, and then for the residual versus fitted value plots, what we could do is we can try a log transformation and see if it could have better results. And also there's another improvement technique, which is the variable selections. So for this time, I use the autoregressive linear model with the combinations of the store size and the store type as my linear regression model. I might probably omitted some of the important variables that has the great influence, have large influence on the Walmart store sales that and then so for improvement purposes, I can try to find what types of variable I missed, and I'm trying to see if I can put those variables back into the regression model and see if it could yield a higher accuracy rate. And so this is some of the improvement techniques that I think I can implement into my linear regression model for application. Thank you.